Okay, good morning. I'd like to welcome you to today's Fields Institute COVID-19 Mathematical Modelling Seminar. We are welcoming Pieter Houtekamer, who will be talking on analysis and forecasting for COVID-19. And I will hand you over to our director, Professor Kumar Murthy.
Thanks, Sarah. So let me just repeat what Sarah just said. Welcome to the seminar. I hope you had a nice long weekend. And all of you were probably busy at work on your modeling. Maybe some of you were. Anyway, we're delighted to have a speaker today from Environment Canada. Our group has been collaborating with various government agencies, both federal and provincial, and that for collaboration has been very fruitful, both in terms of academically as well as in terms of real-time involvement in interaction and policies. So we're delighted to see that kind of collaboration happen and have members of the government also speak to us. So Pieter will speak on analysis and forecasting for COVID-19, please.
Okay, thank you very much. I'll say first, I'll go through this presentation from beginning to end. Usually I don't capture it when you have questions or chats. So you can try to pose a question, but maybe you just have to keep the questions for the end. So I'm working at Environment and Climate Change Canada. So I'm working on weather forecasting, and I've been doing work with some international collaborators with similar backgrounds, so mostly in the geosciences. So the head of this is Geir Evensen, a Norwegian, and I'll be explaining how I got involved in this type of work. Try to go to the next slide. Sorry. So I'll give an introduction to the talk, and then I'll say a little bit about COVID-19, what are specific properties of a disease that are important for the modeling. I'll describe the model we use and discuss the kind of strategies you can have to control or not the disease. I'll be using data from Quebec, and we use this data to make an estimate of parameters and then do some forecast experiments. And at the end, I'll have some discussion on how we think we can improve the method. So essentially, I would like to do something similar to what's being done for many years now in meteorology. So numerical weather forecasting started around 1960. And since that time, we have seen very big improvements in forecast quality. And essentially, we have been doing always the same type of thing, but gradually improving as we go. So what we're doing is we're trying to track the state of the atmosphere. So we do very short forecasts. We do 6-hour forecasts, and then we compare with new observations. And we try to have an optimal combination of the observations with the state of the atmosphere. And then we again do a new 6-hour forecast. And every once in a while we do longer range forecasts for the general public. So I think weather forecasting is really like a perfect type of science, in that you can see very quickly when you need to improve something, because then your forecast goes wrong. So for me, this work started on April 10, when I got an email from a colleague, Geir Evensen, who was trying to predict the evolution of the COVID-19 epidemic in Norway. So there, the concern was if they could open schools or not. So then he made code available on GitHub. So me and a number of colleagues, we've been trying to use this code for our respective areas. And the results so far is a preprint that describes that the work that has been done in all of these countries. So you can find this now on the web. But today I'll just be presenting what I did myself for the epidemic in Quebec. So just very briefly about this disease. It was discovered, I'd say, in China, in Wuhan, where there was the first major event of superpropagation. So then it became well known. It would seem the transmission is mainly by droplets and aerosols. And the problem with the disease is that even patients who do not have any symptoms that you can see, they can still transmit the disease. Another problem is that it's very hard to identify that somebody who's ill is actually COVID-19, because there is many possible symptoms like fever or dry cough or fatigue that can occur with many other diseases as well. And then the tests that we have, they have the problem of false negatives. So even, so I have one study here that's showing a rate of false negative of 38%. So a patient may think he doesn't have COVID-19 and not quarantine, and then still infect other people. So this is like a global overview of the first part of the epidemic. This is from the Worldometer, showing the number of new cases as a function of time. And you can see some initial epidemic here in China, and then the Chinese took very effective action. So then it was controlled in China very quickly. But then it had been spreading already to other countries where we first had exponential growth. And then there were restrictive measures being put in place, but these were not entirely effective. And so the disease has continued growing. Well, one important aspect of the disease is the age sensitivity. So first here, I'm looking at the age sensitivity for the confirmed positive cases. So then you can see, and these are data for Quebec, that there is people from pretty much all the age classes. So like say a very big fraction of the chart here is for the working population. If you then go to more serious stages of a disease, you see a shift. So here I'm looking at people who need to go to the hospital, and majority of people is 70 years or older. And eventually, if you look to fatalities, it's even more extreme. Then you can see that people who die from this are in big majority 70 years or older, or even 80 years or older. It's 75%. So this is something, this age stratification is something that's desirable to also have in a model. So first I'll show a very simple form of the model we're using. So this is a Seer model where we have 4 classes. I'll be adding more later. So there's the healthy people, the susceptible people who have not had the disease yet, but who might get infected. Then there is people who have been exposed to the disease, but they're not yet ill. So they're in an incubation time. After that, they become infectious, so then they can transmit the disease. And eventually they go to the recovered stage here. And you can see from these arrows here that we're assuming that one can have COVID-19 just once. So just looking now at these same simple equations to look at the phenomenon of growth. So you have growth of the epidemic. If the number of exposed and infected cases increases, and this happens if this term AS minus B bigger than 0. So ASI here is the change in the number of healthy people. So the people who get infected, but it's proportional to the number of healthy people and the number of infected people with some constant A. So this constant A is very important because that's the constant that you can control by having restrictive measures. And then otherwise, evolution is it's just people move from one category to another. So after certain incubation time, people move to the infectious class, and after a certain infectious time, they move to the final class R. So the model we're actually using is a little bit more complicated. There is additional categories here, and also there is age classes. So if you look here in the vertical, you see age classes. So we're grouping by 10 years of age. And then in the final stages, we have mild, severe, and fatal categories for the disease. So you can see category Q here, which is for quarantine. Then there is the additional category for people who die. And there is a category for hospitalization. So people who are either severely or fatally ill will go to the hospital, except there is one exception here, which is very important in particular for Quebec. So there is people who are fatally ill and who do not go to the hospital because they are already taken care of in care homes for the elderly. So they're not counted in the hospitalization statistics. That's why we have this separate category CF here. So we can also write this down in equations. So this is from the paper that I gave a reference to at the beginning. So what I want to show here is that we have this reproductive process, which is given by a matrix. So there is interaction coefficients for each two age classes. I've not done this myself, but you could do this, for instance, to model having more infections between groups of children or between groups of elderly people, or whatever is appropriate for your situation. And the other thing I want to mention here is that you can see the transition. So initially, for the susceptible, exposed, and infected classes, we have age classes, and then we have a transition to mild, severe, and fatal classes. And as I mentioned, there is this category C for fatally ill people. So now, with regard to strategies, as the error growth is exponential, there is essentially two types of solutions. There is either exponential growth until most of a big fraction of the population has been infected. So if that happens with this disease, which is a severe disease, well, there is severe consequences. So for Quebec, well, there's many unknown parameters, but you could think that if most of the Quebec people get infected, that there are for order 50,000 fatalities. So that's, of course, something that one does not want to happen. And that's why I call this an educational forecast. So this is a forecast you could issue if you judge it appropriate to warn people of the consequences of not applying restrictive measures. Then the other type of outcome is what's shown here. That's from Thomas Preo, who has on Medium, he has a number of articles that are I think very illuminating to newcomers to the field like me. So here we have two phases, or maybe three. So initially there is the rapid exponential growth, and then people take drastic action. So there is restrictive measures, and then new infections stop due to these very drastic restrictive measures. And then in the meantime, people prepare for the next stage, which is called the dance here. So they're organized the healthcare system, testing and tracing facilities and things like this. And then after 3 to 7 weeks, there's not many infected people anymore. So then there's the phase of the dance, where you can you can just have the most important restrictive measures, and you can relax on other ones. And if something happens, if you have new cases, then you can take local additional measures. So this can actually work, I think. So example here is for Norway, but there is other countries with similar results, like China, for instance. So first in March, you have this growth of the epidemic. And as you recall, on April 10, I got this email from my colleague in Norway. But then the Norwegians were very effective in implementing restrictive measures. So very rapidly, the epidemic died out, even though they opened schools and daycares. And however, it's not completely gone. So you can see occasional new cases. And in fact, just very recently, they had a big new case as they had permit cruises to operate. So there's been an event on the cruise ship near Norway. So now just recently, they had quite a lot of additional cases. So myself, I'll focus on the situation in Quebec. So there are several reasons for me to do that. Well, there's the question of data organization. So this is done by province. In Quebec, it's the INSPQ. Every province has its own particular situation. So I think it helps to be in the province itself to actually understand the data. Then the second point is that the epidemic with the confinement we're having can be considered like a local epidemic. So then you can, it's justified to look at one region in isolation of others. Also, the response to the epidemic is very much local. So in Ontario, they're doing different things than in Quebec or in New Brunswick. And finally, of course, as you know, Quebec has been hit very hard by the epidemic. So I'll be looking at three types of data. The first type is the number of confirmed cases. So this is updated every day on the website of the INSPQ. You can see initially in March, there is a rapid increase in the number of cases. Then through April, we have about 1,000 cases per day. And then eventually in May, numbers start coming down, and they're now reasonably low. And they're now around like 150 per day. But still the epidemic is still active in Quebec. It's just 6 times less active as before. You can see this bluish area here, which reflects reporting delays. So there may be some time between actually going for a test and getting the results from the lab, and then also having this result on the website of the INSPQ. So there's a delay of say about 4 days or so. So a problem with this, with these observations, is that we don't know what's the fraction of cases that has been tested. So initially, there was not enough tests, and it would be very restrictive in groups of people being tested. So we're assuming in this study that only 15% of cases has been tested. So whenever we get the number from the INSPQ, we divide by 0.15, and then we use it in our study. Should note here that this is not stable in time. So initially we had to limit mostly to travelers, and then recently we also asked people going to bars to go for a test. And now we're asking people returning from a holiday where they've seen a lot of people to please also go for a test. However, this variable is important because there is, as you know, there is delay, of course, between testing, hospitalization, and eventual outcome. So just looking at the number of confirmed cases gives some information of what's going to happen later. Then the other type of data is the number of hospitalizations. So here again, you see a rapid increase, steady increase in March and April. And then in May, numbers started coming down, and they're still coming down. And you can see one discontinuity here. And that's when we started counting somewhat different way. Because people realized that people who had COVID-19 were no longer sick from it, but they were still in a hospital waiting for transfer, let's say, for a place for readaptation or to return where they were before. So on May 20 or so, we stopped counting the people who had actually recovered from COVID-19 itself. So here again, there is some problem with the data in the sense that we have this category of people who go to care homes and stay there when they're fatally ill. I think this happened initially, in particular at the beginning of the epidemic. So I just picked the number of 0.5 for this fraction. Then the other thing, as I already mentioned, it's hard to say when somebody is actually recovered from COVID-19. So there can be kind of fuzzy period of readaptation and recovery. Well, then the good points, well, there's this variable is very well tracked because it's very important. It's very important for the management of the hospital. So, of course, we want the number of patients to be within the capacity limits of the hospital. So this is being tracked very well. And then again, having numbers of people at the hospital will give you some information on the number of people who may eventually die from the disease. So then this is the last type of observation. That's the number of fatalities. And it's given here by the solid line. Again, there is this fuzzy area at the end, which corresponds with reporting delays. So if you look at the total number of fatalities, it's been going up in March, April, and May, and now the number of new fatalities is it's still a few per day, but the curve is now much flatter than it was before. Also shown in this figure is where people came from before they died, so where they lived. So they may have been at home or at places for elderly people or at care homes. So the majority of fatalities you can see is for people who were living in care homes. The other thing you can notice is that if you look at these bars, they are higher than the total number, and that's due to this issue with the reporting delays. So, so to make this, to place in the categories, we use final numbers. Sorry. Sorry about my dog.
He doesn't get permission to ask questions.
Sorry. Sorry, I think, sorry for the noise in the background. My wife is trying to take care of it. Sorry, just 10 seconds. Sorry, so now we're moving to the data assimilation side. So we're now using this data and we're trying to estimate the parameters of the Seer model. So to run the model, of course, you need some people who were initially infected to get the simulation started. And then also you need to know how much time they spent in each of these categories. So for instance, there's the incubation time that characterizes how long somebody stays in the category of exposed people. And then also there is fractions of mild, severe, and fatal cases. And we're estimating the reproduction number as a function of time. So to actually do the estimation, we use an ensemble comment smoother. So this is an ensemble method where we start by creating an initial ensemble with parameter values that we think might be reasonable. So we start with 1,000 realizations that we can run the model with. So then we run our model, as I've shown. We run it 1,000 times. And then for each run, we generate from the model the number of cases, hospitalizations, and death. So then we can compare these model values with the actually observed values. And we can use this comparison to change parameters such that we get better agreement between the model and the observations. So step 2 to 4 here is done in an iterative manner until we get good agreement. And then eventually we get parameter values that give agreement with the data, and then we can run with these parameter values, we can learn 1,000 forecasts with the model. So I'll be doing a few experiments here. First experiment is D, where I only used the reported number of fatalities. And the reporting delay here is accounted for using a convolution function. So that permits having a 4-day delay between the model value and the observation. Then next experiment, I'm also using the number of hospitalizations. And as I mentioned, we're assuming that half of the fatally ill people do not go to the hospital. And then final experiment, DHC, I also assimilate the number of confirmed cases using this 15% fraction between the number of observed cases and the total number of cases. So here I show a result that we had at the end of May when we submitted our manuscript. So with dots, we have observations of confirmed cases, of hospitalizations, and of the number of deaths. And then with all the lines, you can see how our 1,000 member ensemble fits to this. The mean value of the ensemble is a solid line here. So you can see with, I think it's not surprising, with all the parameters that we have, we can fit the data pretty well. Also note, the delay between the number of active cases, the hospitalizations, and the number of deaths. A final note here about this forecast, you can see hospitalizations going up, and that's because what I'm showing is the mean value, and we have some curves with exponential growth, so these count relatively heavily in the mean value. You can see that the forecast uncertainty increases very rapidly when you stop having observations. So for the end of June, we can have anything between a few tens of cases and more than 10,000 cases. The other thing we estimate is the reproduction number R. So we have a prior estimate for this, which is in blue. And here I'm assuming for the prior estimate that all the restrictive measures became effective the same date. It was March 23. And then after that, I use a prior value of 1. So I'm using unity here to not bias our estimate to growth or decay without having any information on that. And then in green, we have our solution. So this is showing that initially, indeed, we had high values for the reproductive number. Then the restrictive measures were effective in lowering the values, but it was only in May that values actually became smaller than 1. This final area here, the end of April, end of May, is not important in the sense that for the final week of the simulation, we have no information yet on the reproductive number because there is time between having actual cases and the prior infection. So there is no way of knowing the reproductive number in, say, the final week of the data. So we really need to look to have data of a few weeks into the future to be able to say what the reproductive number was at the given day. So now I've done this experiment for a number of days where I tried to take a given configuration. I'm using all the data I had prior to that, and then I'm looking how good would I have done with the forecast. So I'm starting here with the forecast that failed. So here I have configuration D. I only have data on fatalities. I'm using data until April 1, and then I do a forecast going 2 weeks into the future. And you can see that what actually happened was a lot worse. So already on April 2, we had a sudden increase in the number of fatalities that we could not have seen coming just looking at the previous data. So we end up after 2 weeks with a big underestimate of the number of fatalities. So the actual number was about 600, and with a forecast about between 100 and 250 maybe. So I've done this for the 3 configurations, DHC, DH, and D. So the point you see here on the right, the first point for experiment D. So the one I showed in the previous figure, where the forecast was a severe under forecast of the actual event. Then I've repeated the exercise every week, and you see for subsequent weeks, the forecasts are much better. So generally, the number of fatalities is within the range predicted by the ensemble. For this first date, forecast valid April 15, we have better forecast when we use some of the precursor information. So when we use hospitalizations or also confirmed cases, then we're able to do a much better forecast. However, if you look at the second part of the period for experiments DH and DHC, then you see that we are over forecasting the number of fatalities. And I think what we're seeing here is that that some of the parameters of the epidemic are changing. Maybe our healthcare system is improving, so that when less of the people will go to the hospital will actually die later. Or also maybe we're now testing, we're surely testing more people now. So we're really inviting everybody to go for a test. So a smaller fraction of the tested people actually turn out to have a fatally ill, fatal version of the disease. So, so we have this problem of overprediction of the end at the end. But I think it's really important to use these precursor variables H and C, because they have information of what's going to happen into the future. And then my conclusion here is that, well, if the system is changing, what I should probably do is estimate parameters using only parts of the period. So maybe I should not try to fit the entire epidemic with a single set of parameters. So what we're now thinking of doing is to use an iterative procedure where we have a number of subsequent periods that overlap in time. So first we would estimate parameters for the first, say, 4 weeks of the epidemic. And we'll probably see that the case fatality rate is very high in that period. But then we would move forward everything 1 or 2 weeks, saving information from our first estimate. And then in this second window, you would use the new data and adjust parameters as appropriate. So then, for instance, you could see case fatality rates coming down. And in this way, you would step forward week by week until you arrive at the current time. So that's very much like we do in meteorology. We're not trying to estimate the state of the atmosphere going back to the 1960s. We're just trying to estimate it now, and then we can use this information now to do a forecast in the near future. So there's other things we could do to have better forecast. Of course, it would help to have more rapid access to the data. So now there's an average delay of 4 days in getting the data. So of course you would gain 4 days in forecast quality if you had the data more quickly. The other problem or aspect is the age stratification. So in the model we have age stratification, so we can look per age class what happens, but we don't have the same stratification in the data. So that's making it difficult to make a good fit to the current situation, where, for instance, in Quebec, I think we have seen a shift in the age stratification of confirmed cases, but now many confirmed cases being for young adults, and maybe when schools will reopen, we will see more children and their teachers. So to actually have such detail help improve model forecast, of course, you would need to have data. Then also, one thing that's clearly missing still is the interaction with experts and clients. So ideally we would have some direction on desired products by clients, and then also we could tell clients what kind of data we need to make better forecasts. So one thing that's very fuzzy in all of this, and that's the fourth item here, is what's done with the patients that have no symptoms. So how do you account for this, and can they transmit the virus or not? So that's all not very clear, and it would be very good to have data on that, so that it then can be put into the model. So this is what I had to present.
Thank you. Thank you, Pieter. So very interesting prospect from really numerical weather prediction applied to COVID forecasting. It's time for open for questions. I think Kuma, maybe you have the first question to ask.
That's one of the few prerogatives of being the director, is you get to ask the first question. So very interesting talk, Pieter. Thank you very much. I wanted to know, even rather than trying to give precise numerical predictions, does your model or model similar to that help us to understand qualitatively what might happen? In other words, should we expect big increases? Should we expect oscillation? That kind of thing. Is there something either in the nature of the structure of the equations themselves or in the initial parameters that would help us to say something about that kind of situation?
Well, if you look at these equations, so this one here, so essentially there is two types of outcome. Either events go completely wrong, so you have uncontrolled growth of the epidemic if the reproductive number stays above 1. Or the other thing that can happen is when you have no growth, then you have a small number of cases, and it will just get smaller, and you will have a solution like you've seen for Norway. And there is very little in between. So it's not like weather, where naturally you go from warm weather to cold weather to warm weather to cold weather, etc. It's forever like this. So I think what we're hoping to have is the controlled phase until there is protective medicine. And the only other solution is that we lose control and that you get a very large number of cases.
Now, actually, Kuma, to echo your question for Pieter, in the SARS period time, and 2003, 2004, our group produced some work that showing why modern epidemic has always shown multiple peaks. I mean, oscillations compared with single peak situations in some of the classical model and also some of the historical epidemic. One of the possible reasons that we show is possibly because a behavior change. So when you see the number of deaths going down, then you relax and increasing the activities. And when you see the cases going down, then you are going up, then you tighten up. So that's behavior change mediated by the reported cases of hospitalization or deaths would have significant impact on the sedentary patterns. I don't know if there's something to do with anything to do with the questions that they asked.
No, that's exactly what I was thinking about. But how do you, what change do you make in the model to incorporate a behavioral change?
In our case, that's a simple case, kind of mechanistic model that explain why there are two outbreaks in Singapore, in Toronto, during the SARS time. You simply change the contact and assume it's not a constant, but it's a monotone function of the reported cases, or the hospitalization, or the death. But that actually tells you, because Peter mentioned some delay from the infection to hospitalization to the death. That shows that in different period of time, maybe you should emphasize on different numbers. So now you are telling people there's if you, for example, try to emphasize on the death hospitalization, then there is a delay, and that change of behavior would be different than the change of behavior if we emphasize on real cases. So.
Thank you.
Okay, thanks.
Peter, I have another question. I know two people are waiting for. I'm taking advantage of being the host. You mentioned you used actually the age stratified population model. However, so in your model, you have this RIJ, the reproduction
Yes.
from one age group to other. Did you estimate this, or how do you?
So
just really, the question you say you don't have the data.
So so now this matrix is just a constant, and it's the same for all interactions. I've experimented with a matrix where I had more interactions between elderly people, because I saw there were lots of cases in care homes for the elderly. But then based on the data I had, I could not see that I was getting better forecasts. And also other people in our group, so for instance, Pierre Evanson himself, he had increased R for the younger age classes to simulate the opening of schools. So in forecast mode, if you know what measures are going to be taken and how that impacts the R matrix, then you can run your model with that.
So you presume certain R and then you run the model. You did not estimate R.
I did not. I just estimate some global value. Let's see. As a function of time, but I did not estimate all the matrix elements.
Okay.
So I think to do such things, I would really need age stratified data.
Right, right.
but I think it would be very important because then, for instance, now we have more growth due to, say, young adults going to bars. Then you could put that in an R matrix.
It is amazing that InSpeak does not release those data. I think Ontario has those data now.
Sorry, I didn't understand your question.
I think the Quebec government did not release those age stratified data.
So, so I have no access to this data. I wrote to the INSPQ and to authorities twice now, and they did not reply to that. But sure, they have the data because they're able to produce figures like this. So I would really love to have access to this, or data like this.
Thank you. So let me pass on to other two colleagues. And Nyayashi, as our last speaker from the seminar. So.
Hello. Hey, thank you very much for the very nice talk. So I just had one question and then a comment. So one question was, how many free parameters do you have that you fit to the data?
So there's about, I think the number is 13, but then this reproductive number can change as a function of time.
Okay, so that could actually change as a function of time at any time, the reproduction. I see. Okay.
Yeah. So then, yeah. So then you.
So then, what would you do for the future then? I mean, it could do anything it wants, the reproduction number in the future.
So in the future, I keep using the final estimate I have.
Oh, okay, the final estimate. Yeah. So I have one suggestion regarding basically the change of behavior, and I think this is what I talked about a couple of weeks ago. So Google now releases publicly the mobility information from basically for various places like workplaces, retails, transit stations, etc., as a function of time, and it releases it periodically. I think it has it all the way to the end of July now. So this is something that in principle would modulate all these parameters, in particular the reproduction number, because of course the more people go to workplaces, the more, or to retail, for example, retail stores, the more disease would propagate. So I think maybe one way to come up with a more predictive model is to use this type of information from Google, and also possibly the weather, which, I mean, of course, the better the weather is, the more people could get out. So that might be one way to kind of come up with a more predictive model. What do you think?
Well, I think I would maybe then start by looking how well these data from Google explain what we have seen already. Mm-hmm. So don't have it into the future. With regard to weather, I think the interaction is really very complicated. I think warm weather in principle is good for limiting growth. But on the other hand, if there's more air conditioning systems being active and people staying inside, then maybe it may have opposite effects as well. So like currently we see a lot of growth in the south of the US. So I think the link with weather is not very clear to me.
Yeah, so our analysis shows that, I mean, there is dependence on weather and on mobility. And of course, in south of the US, they are opening up, and that's the main reason, in spite of the weather. But yeah, so that's it for me. Thank you very much.
Okay, thank
you. Monsieur Professor Yifan, if you have a question, you have to unmute.
In your the model, you added also the new component die.
Yes.
And then I would like to know that yes, and if you go and then I would like to know that if, for example, you list only the people who died in the hospital. How about the others?
Well, I also have I have statistics on the total number of people who died. So both at the hospital and the care homes. So every day these total numbers are being released. I don't actually have the fraction on a daily basis. So I have let's see, where's that? Sorry. So I can see from the published data where people came from before they died, but I cannot see if they have been at the hospital or not.
Mm-hmm. So it could have impact for the forecast, right?
Yes.
So the other questions related to the model, because in the regional level, like in Quebec, one can consider instead of your deterministic model also stochastic, because for the stochastic model, there is also very good the algorithm for parameter estimation. What do you think about the stochasticity in comparison with your model?
So now we model uncertainty by having 1,000 members, but that indeed every member itself runs a deterministic model. I think having stochastic model error or terms in the model is important when we go to a procedure like we have here, where we try to use subsequent data assimilation windows. So then we may need stochastic terms to maintain sufficient spread in the ensemble.
Okay.
Okay, so I have one final question before I pass on to Kuma. Pieter, so you have been doing the weather prediction, now you're doing this for epidemic prediction. What did you feel compare these two predictions? And
well, I find that epidemic prediction is much more difficult. Mm-hmm. In the sense that everything is changing all the time. So how people respond to something may change, the virus may change, the healthcare system may change. Whereas the weather, it's easier. It's still the same laws of physics as we had back in the 1960s.
Yeah, so a lot of uncertainties. Yeah.
Okay, we count on you to tell the government about that. Kuma, I pass on to you. Thank you, Pieter.
Thank you, Pieter. Very interesting talk, very good discussion. Thank you, everybody, for attending. It's very interesting, you know, once humans are involved, things become a lot more complicated because you have to somehow incorporate the behavior into the model.
Yes.
That's a very interesting comment you just made, because many of us think the weather is very complicated.
Yeah.
So thank you very much. One nice thing I like about this seminar is the way it's drawing in people with different backgrounds to wrap their head around what's going on now and to share their expertise with respect to the modeling. I think that's a really big strength of this seminar. So thank you, all of you who are coming from your different backgrounds and participating. So that's it for today. We meet again next Tuesday. Thanks again for coming. Let's join me, please join me in thanking the speaker.
Well, thanks for listening.
Bye.
Bye.
Bye.